So this talk is just about this form. The font should be large enough. Yeah, as you can see, we're trying to solve some of one-dimensional convex function, but with a bunch of A transpose X. The only difference is here we only assume Fi is convex, so it can be non-smooth. For example, you can put some L1 term inside, and that's why I don't separate the regularizer and the form, because you can just put everything on Fi. And our goal is to get a running time depending on n plus d and a bunch of log. And so what is the previous result? So currently the fastest running time has two types. One type will depend on some condition number of the form. For example, if you assume the function is smooth and strongly convex, then you can have a very good running time. The running time is n plus some smaller order term. But if the function is not smooth, then kappa can be infinity. And if the function is not smooth, then the best result is the cutting pin method. The running time is n cubed. And in this talk, we focus on kappa equals to infinity case. Also, we focus on the case n is roughly d. N is the number of terms, and d is the dimension of the form. And certainly, the case n much larger than d is much harder. It is too difficult for me to solve. So we focus on a simple case. And so what is the best running time for this case? So the simplest form for those cases is you just replace the Fi by square. Then this is just a least square form. And for least square form, if we don't assume anything about the matrix, what is the fastest running time? The fastest running time is just use the matrix multiplication, so the running time is n to 2.38. And this year, George proved using the current technique, the best you can hope to get is 2.168. This number will show up later. So our result is this. Let's say Fi is L1 Lipschitz, the domain size is R, and all the AI is bound by L2. And our running time is this. We'll get the delta L1, L2, R error in time. The running time is very long. So the first term is just the cost of multiplying two matrices. The second term is something difficult to explain, but the third term is easy to see. The third term is just 2.166. Just to explain what is the second term. So alpha is the largest number such that multiplying n by n to alpha and n to alpha by n matrix take n squared time. For example, if omega is 2, if we can multiply 2 n by n matrix in n squared time, then certainly alpha by definition is 1. So imagine if someone fully solved the matrix multiplication form, then our running time is simply n to 2.166. Remember, the lower bound of current technique is 168. So in some sense, our running time is pretty nice. Also, notice our running time is not dependent on the delta. So in some sense, we don't really depend on L1 or L2 or R if you don't care about log term. For the current bound on omega and alpha, our running time is simply the matrix multiplication time. Many people ask me, can you improve 1/6? In fact, the original purpose of this paper is to improve the 1/6, and we couldn't improve that running time, so we just make the form more general and publish the paper. So I suspect you can improve that if you have 100 pages. Anyway, our algorithm is very simple. It's just based on integral form method. Our main contribution is just give a new proof. So we first give a proof about the results for LP in stock. And this is an alternative proof of the same result. So you can think a lot of iterative method is of this form. Each step you add x by some nonlinear part of some matrix times your vector. It includes Newton method if you do some transformation. And usually the bottleneck is not to apply the nonlinear part, the bottleneck is to apply the matrix to a vector. And usually, because we're doing iterative method, we don't really care about multiplying the matrix and vector exactly. Usually, you approximate in certain way is okay. So our technique is super simple. Since we don't need to multiply the matrix exactly, so we just add a sketch there. So instead of computing m times x, we compute r transpose r times m times x. And r will be a y matrix. Why this is better? Because let's say in the very first iteration, you generate a random matrix R. Now you can pre-compute R times M. This will be a Y matrix. Then in all the step later on, you just need to multiply the Y matrix by a vector, which will be faster than multiplying a square matrix with a vector. Precisely, if the Rm is S by M matrix, then each step will take Sn instead of n squared time. So with this idea and a lot of calculation, you will get this result. So in some sense, the take-home message of this paper is this. If you have an iterative method, you believe your method is robust, and somehow you need to solve many linear systems, for example, Newton method, then usually you can do some trick to make the number of linear systems just go to not many linear systems instead of a lot of linear systems. So I will end this talk by this open problem. So we don't solve the problem when the number of terms is much larger than the dimension, which is the more important case. So the open problem is, can you get a running time n plus poly d poly log? Thank you. Yeah, randomized.
Do you have bounds on the failure probability?
So the failure probability is hidden in the log term, so we pay a log term for that.